Pleasure to present my joint work with Miller and Yaoyun Shi. We are interested in the local randomness in the non-local game setting. So when we talk about non-local game, we usually refer to a game played by Alice and Bob, where they can share some predetermined strategies, but they cannot communicate while playing this game. So one of the most central and counterintuitive aspects of quantum information theory is the ability for quantum players to outperform classical players. And by the loophole-free biotest, it has been shown that superclassical score can guarantee randomness. And this is the basis for device-independent randomness expansion. So here, we ask a related but different question. So what if the other player is dishonest or evil? So in this case, if we can get some high score, can the adversary get my output? So proving randomness in this case could open doors to cryptographic protocols where both the player and device can be untrusted. So our goal here is to first prove that superclassical score can guarantee local randomness. And we want to develop some cryptographic protocols with untrusted device and players. So our intuition here is that if Bob doesn't do any measurements on his local system, then he has all the information required to recover Alice's output. But if they want to achieve some high score, then Bob is compelled to do measurements, and he will lose the information on his side. So the fact that Bob's local system keeps changing marks a difference between our work and previous works. So we started by wondering whether we can give a general bound on Bob's guessing probability given the condition that he have access to Alice's input and they have already achieved some superclassical score. So what we proved is that for the complete support game, meaning that all the input pairs have non-zero probability, we can say if the gaming score exceeds the optimal classical by epsilon, then the guessing probability is at most 1 minus epsilon square. So we can demonstrate this result with CHSH game. So let me introduce the CHSH game first. So the rules are very easy to explain. And basically, Alice and Bob each are given a random bit, and they are asked to respond with 1 bit as well. And the winning condition is that the AND value of the input bits must equal the parity of the output bits. So with classical strategy, the optimal score is at most 0.75, but with quantum strategy, you can improve that to roughly 0.85. So we get this plot. The x-axis is a gaming score starting from 0.75 and goes to 0.85. And the y-axis is maximal guessing probability for Bob. So you can see the curve is starting at 1 and goes below it immediately. So the essence of this plot is that it clearly indicates true quantumness can give you some randomness, meaning that Bob cannot guess Alice's output perfectly. And it also implies that if it also implies if we combine Alice's output with Alice's input, it's more random to Bob than Alice's input themselves. So there's a potential way to expand local randomness. However, there's one drawback of this plot. If you look closer, you can see the endpoint is roughly 0.996, which means this bound is not numerically very strong. So in the next part of the talk, I will give 2 different methods to give stronger bound for specific games. The first one is the NPA hierarchy applied to the CHSH game. And the second one is a rigidity result of the magic square game. So let me start with the NPA hierarchy. This part is a bit technical. And the NPA hierarchy is an infinite series of conditions which will converge to the set of quantum correlations. And within this hierarchy, our problem becomes a semi-definite program problem. and which was introduced by Jimmy on Wednesday. And let me say something to remind you about it. Basically, it's very similar to linear program. And you can imagine turning a linear program into a semi-definite program by replacing the vector inner products with matrix inner product and replacing vectors with positive semi-definite matrices. And this part is the instance of the semi-definite program, which is also called a certificate in this hierarchy. The rows and columns should be labeled by projective operators for Alice and Bob. Here, A's and B's are the projectors they use to play the CHSH game. And the B primes are used by Bob to guess Alice's output. And in the subscript, the first 2 bits are the inputs to the game, and the last bit is Bob's measurement result. So each entry in this certificate should represent some probability to measure a certain sequence of measurements. And for example, this one would be the probability to measure the sequence B00 and B prime 00, given that they share some purity psi. And one thing to note about these projectors is that A and B's commute, but B and B prime does not necessarily commute. So because they are applied sequentially here. And so our application is different from previous applications where they are considering quantum correlations from commuting sets of measurements. So we use third level certificate and applied some semi-definite program solver, and we got this plot. So the y-axis and x-axis are exactly the same. We got the upper bound, the blue curve, is starting at 1 and it goes down to 0.85, which basically means when you have the optimal quantum strategy, the guessing probability is the same as gaming score. And you can see this one is much more tighter than the previous one. And to actually show this one is tight, we come up with a lower bound by considering a probabilistic mixture of the optimal quantum strategy and the optimal classical strategy. So the optimal curve for Bob's guessing probability should lie in between the blue and orange curve. So the second method is the rigidity result of the magic square game. And we didn't apply the NPA hierarchy because the calculation is a bit expensive here. So in the magic square game, Alice and Bob are each asked to fill in a row or column of a 3x3 box with 0 and 1. And the winning condition is that the row must have even parity. Sorry. Okay. So the row must have even parity, the column must have odd parity, and the overlapping boxes must match. So you can see the configuration in this slide will score 1 for this game. And the classical score is at most 8/9, but with quantum strategy, it can be improved to, with quantum strategy, they can win every time. So this slide shows the optimal strategy for this game. Basically, they will share 2 EPR pairs, and they will apply the Pauli operator according to these 2 figures. And what's interesting about this optimal strategy is that when they achieve score 1, Bob cannot guess all the Alice output bits. So let's say this example, if Bob got 0, 0, 1 in the first column, then Alice output for the second row could either be 0, 1, 1 or 0, 0, 0. So Bob's local CA in this case will be the same across these 2 settings. And basically, when he knows the first bit, he loses information about the next 2 bits. So we think maybe if they share some close to optimal strategy, they can, Bob's local system will be almost identical, something like that. So we start by looking at this rigidity result, which is saying if the strategy can achieve score 1 minus epsilon, then the distance between this strategy and the optimal strategy is of order square root of epsilon. So we prove this that under same condition, if the score is 1 minus epsilon, then the trace distance between Bob's local CA is square root of epsilon. And we combine this with the observation that Bob's guessing probability is upper bounded by the probability that he can distinguish his two local states when Alice applied two different observables. So we say that, so the guessing probability is at most a half plus square root of epsilon. And when epsilon goes to 0, this will go to, so Bob will have no knowledge basically about the last 2 bits. And inspired by this proposition, we come up with an application It's called the Deletion Certification protocol. And imagine Alice has some message that she would like to send to Bob. So first, she can encrypt the message, prepare the decryption key, and give the encrypted message to Bob. At this point, she could have 2 options. The first one is that she could just give the decryption key to Bob so that Bob can read the message. Or she could tell Bob to delete the message and send back some certificate to certify that he is honest and deleted the message. To make this protocol more feasible, we require only classical communication involved. And the inspiration from the proposition is that if something is inaccessible to Bob, then it's the same meaning as something is locally random to Bob. So we developed this protocol which consists of playing n rounds of the magic square game. So here's how it works. Oh, sorry. Basically, in summary, Alice have 2 options, either to decrypt the message or certify the deletion of the message. So here's how it works. Alice will first generate 2 sequences of random numbers as inputs to the magic square game, one for herself and one for Bob. And then she will play the n round of the magic square game, and then she will choose a random round and a random bit in that round to be a secret bit XOR to her message. So if Bob can figure out this secret bit, then Bob can basically read the message. And so if she wants Bob to know the message, she can just give Bob like what's the round number of this round and what's the position of the secret bit and Alice input to this bit. Of course, if Alice would like Bob to delete the message, she could move on to the deletion phase of this protocol. She will give Bob's output to Bob and then ask for Bob's input to Bob and ask for Bob's output. So, and then she will check her output against Bob's output to see if they have scored at least 1 minus epsilon in this game. And if they achieve score minus 1 minus epsilon, this certificate will be accepted. Otherwise, the certificate will be rejected. So why this protocol will work? Basically, we first use some martingale argument to show that Bob is very likely to be honest if they can pass, if his certificate can pass the test. And then we can use the previous proposition to show that if Bob is honest, then his knowledge about the secret bit is very small. And since the case that Bob is dishonest is very negligible, so we can conclude that when Bob can pass the test, then, and when the number of rounds goes to infinity, his knowledge is 0 for the secret bit. And basically, what we achieve is that if the deletion is certified, then the resulting deleted state will be unreadable, even if Bob can have the input bits afterwards, or the decryption key afterwards. So in conclusion, we have shown that superclassical score can guarantee randomness, and we have demonstrated different techniques to give stronger bounds on the Bob's guessing probability or on the local randomness. And in the future, we are thinking about how to accumulate local randomness over multiple repetition of a non-local game. So this ends my talk. Thank you.